Hi, everyone. Okay, we can start. So this is the talk where we actually introduce the ET platform. What the ET platform is a fully open source manycore platform. What does that means will be what is going to happen after this talk. About me, a lot of things I can say, a lot of things I shouldn't say. The older I get, the harder it becomes to explain what I do. So I would say that hypervisor operating system and security is where I built my career on, but I've been doing a lot of random stuff. For the past few months, that felt like years. I've been doing software at Ainekko, and of course I tend to gravitate towards what is my comfort zone, we would say, which is that gray area between hardware and software. You can find more about me if you're actually curious. And about this talk. So what I wanted to introduce in this talk is ET platform is very complex because it's a full compute architecture that is extremely software defined. So the software, everything is open source right now, at least from the runtime to the firmware. The manual to describe the hardware in gory details is there. But I actually wanted on this talk to be a bit more theoretical, to just show, and so where you can guide after you have access to everything, what you're looking at and how it's supposed to work. So we're going to start with looking at how can I use the software at the lowest level of the stack, which is the runtime, and how you can get to run stuff on this course. And then we're going to start from the board and then go lower level until we hit the single CPU. Then I'm going to point out where the software is, and then also how can you help and how can you fun with this, at least the same amount of fun or more than we had in the past few months that felt like 2 years. Right, so this is how the software look. Essentially, you can see that the skin is divided in two. You got the hardware side and you got the software side. And it's interesting to look at this like a hourglass, because essentially like you get to the software, but then you get to the hardware point, but then you have more software that runs there. So the highest level that usually people interact with in this is the runtime library. So the runtime library is actually both simple and powerful because it allows us to, essentially the model that we have is that you compile health in this for these cores, and then you load them in the device RAM, and then you can just tell them to execute. But he also has some basic synchronization approach, like he has the concept of streams and events. And what is important to say, these are actually RISC-V binaries running in user mode, so they're actually full complete CPUs. Going down the stack, the things that are interesting is that there is a device layer, which is a device abstraction layer. And what's exciting for us is that there's both a simulator for the card and it speaks to the Linux driver. Linux driver exports two devices, and one of them is for the control plane and also to get information about what's happening in the system, and the other one is to actually communicate directly to the compute shires to tell, now do this. And of course, the memory is mapped, so you can actually load the core and the memory on the machine. And this is how it works. What is interesting is that you will see there's a service processor that actually has a device API, and in general, like the whole mechanism to at the very lowest level of the operating system is to actually is message-based, and everything and all the API are open source. And you can actually change it as much as you want. But let's have a look at the hardware. So I wanted to get the developer board here, but unfortunately our CTO has parked a forklift there, so I cannot access. But this is one of the board, and if you remove the big heatsink, you will see everything here that is actually important. So the star of the show, of course, is the ET-SOC 1 chip. You get 4 LPDDR, 4, and then you actually get, and this is an actual board for professionals, so you actually will get the FTDI chip that conclude the things, and actually another microcontroller, which is the power manager microcontroller. So what do you do and how do you get and how you interact with them? So the PCIe, of course, like the ET-SOC is the one that controls everything. He has the PCIe interface that the lanes go directly into the PCIe. Of course, he has access to the memory, but also he has this strange relationship with the power management controller, because the power management controller is the one that controls all the voltage regulator. And so you can actually so you can actually also tell to change the frequency, to change the voltage. But then the things that is very useful for us when we're debugging the system is that there actually a UART that gets both from the ET-SOC and the PMIC. So you can actually interact live with the PMIC because it has free RTOS running on it with a prompt, and you can just destroy your card as much as you want, which is actually fun. I can tell more about how the weird states I put the card into if you're curious. Right, so when you actually look at the ET-SOC 1 chip, what does it look like? Because yes, manycore means a lot of things, but what does this look like? So the core of everything, of course, is the network on chip, which is the kind of technology that allows us to do this kind of stuff. And so there's a network on chip, the network on chip that connects everything. You can see that there's definitely a device bus that connected to the thing that has the PCIe, the USB, the eMMC, the UART, and I2C, of course, you need that. You got a DDR4 interface, and then you got the service processor. The service processor is essentially the microcontroller that can actually control the board. In fact, it has its own separate device bus that actually has the connection to the PNC, has the GPIO for configurations, and also has its own separate UART, because each one of these things actually run their own firmware, so you can actually debug it, which is quite important. And then the things that are missing, which is the most important part, is the compute shires. And they're called shires. We're going to go there on why they're called like this, but essentially is the core is a set of like 1088 cores that of RISC-V generation that actually do the compute. And they're sitting on a NOC, they're waiting to get messages, and then they just execute the kernel that they access to the DDR4. One of them is named the master shire, and is the one that actually that actually communicates with the host and tells on the compute plane and tells what to execute and when. The amazing thing about this architecture is that actually software defined. So this architecture, this name, everything about this is not set in stone. You can change whatever you want. And thanks to ET platform, you have the tools to do that. Now let's have a look at what a minion is. A minion is a normal RISC-V CPU. It's RISC-V 64 IMFC. So what is missing to becoming a generic, a G RISC-V is the atomics. And the atomics in here are actually specifics to the architecture. They're actually very similar, but they're split in two because, as you can imagine, a system like this, and I can go on and on if you want, the memory and the way you actually handle memory and the coherency across the system can be very complicated. So they have atomics for local, meaning at the L2 level for the shire, for the group of 32 cores, and the global that actually impose coherency on everything. But they do have atomics, so it can be a GC. You can run Linux with minimal patches on this. And then you got some vector instruction, which is packet float and integer instruction that are Esperanto specific. They're much simpler than the RVV, but that's another kind of worms you can open whenever you want. But then there's also tensor operation. There's actually an accelerator in each of these 1088 cores that actually can do very complex matrix and tensor operations. And yes, it is a generic RISC-V machine. You actually will see the source code of the machine mode software that is running on it. You will see the supervisor, the kernel mode that's running on it, and you can run whatever you want on it. And then in the usual scenario, that is how the software is now set up, the compute kernels actually run in user space. But nothing is set in stone in this architecture. So this is where things get interesting, right? Where do you find things? So being open source, we actually have the full details of the chip online. And you can actually open it up and it will describe way more that you want to know about this chip. But what's important about it, you can use it, you can change it, you can run it, and you can even simulate it if you don't have access to the card. But if you speak to Roman and you're nice to him, you probably have access to one of this card in some ways. What the job that we did in the past few weeks or months that felt like 2 years, we definitely ported GCC to compile on Minions code with all the extension to the master, and it's this RISC-V new toolchain, so you actually have a full toolchain when you compile it. we actually open sourced the platform software, and this contains everything from the runtime to all the firmware, to everything that is running on these cores, on the shires, on the service processor, and you can change anything you want, and you can experiment with the card, and you can see what happens. And then we actually have ported as a test Llama CPP, and it is something that actually shows how this architecture is actually very easy to work with, because the truth is, when we port Llama CPP, we needed to write the kernels, but being generic CPU kernels and being a proof of concept, we could just take normal C code and run it as kernels, and it works, and it can actually offload things. It's not accelerated, but that can be done. But it kind of shows the kind of power that this architecture has. And so this is possibly the last slide. This is open source acceleration, because actually everything, and I think Roman can comment about what's more to come, but definitely everything is open source here. Like, it's actually, for me, it's been really fun to be able to have an hardware, connect to USB, and see what the PMIC was doing, and say, actually, I don't like this, I can change it, and I can add my own command for test or something. And then you can actually play with the PCIe and see what happens, or you can just change how you schedule things. Like, the truth is that when you have this machine and this architecture and you have all the control of the software, you have 1088 RISC-V cores on your PCI bus. And actually, the peer-to-peer DMA, so they can actually get the master of the PCI and just control and just communicate with everyone. And so this is, I know that this is, of course, is going to be AI specific. It's an AI accelerator, but it's way more than this. It's actually like a compute platform. And when you like to play with hardware, as I do, this is kind of exciting for me. And yeah, so we have, of course, shockingly, some issues we need to work on the card. It's not perfect yet. And of course, what we're trying to do now, and we're setting it up, is to work everything on this level, on the hardware level, on the software level, of suggestion of how to modify the runtime to allow better workloads or different workloads, or a generic computer architecture, or on GitHub. And what I'll be doing is I will post in the known bugs that I'm pretty sure are the only one that exist online, and we'll try to make everything open. So, as I said, this talk was mostly about the giving a guide to what is going to happen. You can definitely go back here and see all the code, and just stop me if you're curious about it, because I'm going to go on and on about this for hours and hours and hours. So just let me know, and there's a lot of fun. And I repeat, even as today, you do not need a card to play with this system, because you have a simulator. Let me know if you have any questions about it. None. Great. I was so clear. Oh, no, there is a question.
I guess just a simple question. You say it's very reprogrammable, shuffleable architecture. Is what's like the overhead of that? Like of the programmable.
Can you repeat the question, please?
Now, what is the overhead of the programmability? Well, it's very fast, of course, right? No, I'm joking. So it's up to what you define by overhead and what's the baseline you're considering, right? So, of course, if you have a systolic array that just do one operation, is going to be very compute dense, right? What you have here is the ability of actually modify the core as you want. Like, I believe that this card originally started as a graphic CPU. In fact, you still find some very strange cube map and cube face instruction set in it. But then it could change directly into this. So it's up to what you mean. Overhead in terms of like, size of the chip. Of course, it's less compute dense, but it's more like the bet is that being this generic, it can actually allow to have workloads. We cannot think about it yet. In terms of software, well, it's actually quite simple as a messaging stuff, because essentially like what you have is like, for example, the service processor, the minion cores, they all have some mailbox that communicate directly with the host. So unless you decide to have a JavaScript VM that just need to handle everything and do an HTTP server request and then send it, which you can do it. Like if you actually use this, right now, what we see in the current software, which is not simple, actually the performance, of course, we're still in the lucky position that we are memory bound in our calculation, which is where you want to be. So actually, no, the overhead is relatively small because the hardware allows you to be that. Okay. Well, I guess now Justin is going to see how to actually use this for AI, which is probably more exciting.